Good afternoon. My name is Ali Kujuri, those of you who don't know me, and I would like to welcome you all to this sixth lecture in the ES Engineering Science lecture series, and for this academic year. And in fact, this is the 117th lecture since we started in 2006. I would like to thank also Keysight Technologies for sponsoring this lecture series since the start. Before I introduce our guest speaker for today, let me mention that we have ordered pizza, and it's going to arrive at 5:30, and I hope that you all like it, and our guest speaker will be here also to enjoy the pizza. The next talk will be on February the 2nd, because very soon the exams are going to start here, and we'll be having a speaker from, in fact, Keysight Technologies. But the title of the talk and also the name of the speaker is to be determined. I'm right now communicating with Keysight. Our guest speaker for today is Dr. Ahmed Amer, and the title of his talk is Sustainable Storage: Approaches to Efficient and Practical Storage Reliability at Scale. Dr. Ahmed Amer is an associate professor of computer engineering at Santa Clara University. His research areas are systems, particularly storage systems, operating systems, and distributed systems. His work has included the predictive management of data and storage, with recent work involving data grouping and the management of shingled magnetic recording technologies, the design of highly reliable systems at scale, and energy management. He is especially interested at alternative and upcoming storage technologies and their most practical and effective applications. So here is Dr. Amer.
Well, first of all, thank you very much for having me over. I'm deeply, deeply honored to be here. I'm very grateful to Professor Kujuri and Professor Figueroa for inviting me, and for you for bearing with me through this. But what is this? That's really the question. What are we talking about today? I called the talk Sustainable Storage, partly because dubbing things sustainable makes it sound cool these days, right? Yeah. Right. No, but seriously. Allow me first to start by perhaps introducing myself and mentioning what I work on. Well, I work on data storage. I work on reliability problems, and I work on energy efficiency problems. I'm an operating systems guy, which means I try to look for ways to automatically be as cheap as possible, because that really is what it's about. It's about expending the resources you have in abundance to save and make the best use of the resources that are scarce or the resources that are expensive. Whether you look at that in terms of caching storage, or whether you look at it in terms of managing a new kind of storage technology that's going to work out to be cheaper per unit volume versus another. That's really what you do with system software, right? So why do I work in this area? If you're looking for a problem to work on, what is its most appealing feature? Anyone? The most appealing feature of a problem to work on. Should it be an easy one to solve?
It should be one that makes you money.
One that makes you money. That is a very, very good criteria, a profitable one. Another criteria.
How many people does it serve?
How many people does it serve? That is a very, very altruistic look at it. How much impact will the problem have? And that's actually another way of rephrasing the same thing. The greater the impact, you expect it to be hopefully more valuable, right? Okay, but that isn't my criteria, the best criteria. The best criteria is if the problem's insolvable, preferably, but everyone wants it solved, or ideally, if it just keeps on growing no matter what you do, right? So that way, the more you solve it, yeah, you've made everyone's life better, and it's valuable, but there's more of the problem to solve, right? So what is that one resource you have that just keeps on growing? The answer? Cat videos. Absolutely. I'm not joking, because think about what's happening with storage, right? I'm advancing my laptop and not advancing this. What will your storage systems look like going forward? The answer is bigger. How bigger? Well, in your personal experience, I still remember when I bought my first 120 megabyte hard drive. Boy, was that cool and impressive. Now I just switched it out with a 2 terabyte hybrid thing. It's really, really nice. It's like, will it hold everything? That's a question that's on my mind, because I, of course, have a lot of cat videos. I jest. I have no cat videos because I do not own a cat and I don't film other people's cats. But that's a serious point, actually. Once upon a time, if you're a photography enthusiast, you would have cared about how many shots you took. You'd been a lot more careful about the framing of a photograph you took, right? Very recently, I was on something called the Monongahela Incline. It's this car, a funicular, a railway on the side of a hill. It overlooks a beautiful city. And it's actually a very, very useful one to take to get between 2 points. Unfortunately, it's also very scenic, so it was filled with tourists. And can you imagine what they were doing? They were taking photos out of the window of the funicular at night with flashes. And they were taking multiple photos. So you can imagine these people will get home and they'll have 30 or 40 photos of themselves in a mirror. But that's a very different mindset from when you were taking 35 shots and worried about when your film was going to run out. So if I told you that the biggest increasing, most rapidly increasing volume of data stored was not videos but flat photos, would you believe me? That doesn't seem to make sense. Videos take up more space, right? Except you think about taking a video a lot more than you do about snapping a photo and another photo and another photo. I'll prove this point to you in a second. But the point I'm getting at is data storage is a great problem to work on. Managing data storage is a great problem to work on, just because people keep generating a heck of a lot of data and they no longer think about getting rid of it. Which means that your storage systems in the future will be larger. They will become more aging because those cat videos have to live somewhere. And while, yes, I can upgrade my hard drive, Flickr upgrading its hard drives is slightly different. Facebook upgrading their hard drives is a slightly different proposition. They're going to wind up with more and more systems that have older components, so the manageability of those systems and the scalability of those systems and how much it costs you not just to build them, but to maintain them over time becomes a meaningful problem. Okay, and part of the cost of maintaining systems is worrying about what it'll cost you when you lose people their data. Which is why when you build them up and start scaling them up, you start caring a lot more about, well, hang on, how reliable are they going to be? How much are they going to cost you to build? What is it going to cost you to make them more reliable? So, okay. Future trends really mean nothing unless you look back at what happened in the past. So here's a photo. So that's why I should recap. I work on system software because I believe it has the most direct impact on the problem at hand. Hence it goes to how much it affects people. And the problem that I work on is data storage, because that is a flood that just doesn't end. It's a very, very beautiful property to have in a problem, but it also means that there's a great need to solve the problem well. And why do I always mention energy every now and then? Because some of the best arguments I see to what is a good policy or a good design looks at the total energy cost of a system over its lifetime, for example. So when somebody tells me, oh, I need a pointer that can point at data that's only 32 bits in length, that can point at a 4 gigabyte space, but a 64-bit one can point at 16 exabyte space. That's a much, much bigger space. So once upon a time, a very great man said, we're not going to need more than a half dozen computers commercially in the country. He was wrong, right? I mean, we have a few more than a half dozen computers engaged in business these days. But there's this counter tendency to then say to yourself, well, I'm going to design it to be super big. I can't design it to be too big. But my favorite argument in that regard was an energy-based one, where somebody looked at, hey, if I built a file system so that it could grow to this capacity, and the capacity was the largest size you could point at with a 128-bit pointer, they tried to look at how much energy would it take to write that much data. And then they said, well, if we're going to expend enough energy to boil the Pacific 3 times over, I think we're going too far with the data we're storing, right? So it gets to that point. So you want to think about the limits, but at the same time, it's a problem that really doesn't have limits when you look at the time factor. So looking back in time, anyone remember this photo? It's a beautiful photo. It's a, I believe that's 20 megabytes being loaded onto a plane, or 10 megabytes, I'm not sure. But why is that relevant to us today? Because at that time, what we thought about in terms of storing data was very, very different from what we think about now. And it's partly a result of how the technology has changed over the last few years. You guys are familiar with the Moore's Law arguments regarding if the automotive industry had advanced like the computing industry had, we'd have 1,000-mile-per-hour cars that run on a milliliter of fuel and never need repair and cost $5, right? That would be, you've heard this analogy. This analogy is often drawing a parallel between the automotive industry and the chip industry. So chip density has grown dramatically over the years. Storage density and capacity has actually grown more, much more, since this photo when 10 megabytes were the thing. Oh, and I'm also interested in data storage because I also care about data surviving for a very long time. I'm not sure if you know where I'm originally from, but here's a clue. Okay. So I also try to convince my students sometimes that this idea that data and storing the data is the important part of the problem is often overlooked. If you were to build me an automatic computer, why would you build a computer for me? So here's a famous one. This is a Babbage engine. This is actually the one that was at the Computer History Museum. That was the twin of one that was built in the Science Museum in the UK. But what's interesting about this one is why the twin exists. It's because the Science Museum in the UK built part of a computer, but they forgot the most important piece. They ran out of money before they could build the most important piece. So one of the co-founders of Microsoft went and said, here, I'll give you the money to build the missing piece, and the money to build the second one for you. And he lent that one to the Computer History Museum. Can anyone guess what the missing piece is? It's actually in this picture, and it's the closest one to a human being. The closest one to a physical human being in the frame. Here's a hint. There's a hand. There's the most important piece. All this they had. They just didn't have this bit. And what this bit is the data output device for that computer. It was the printer. Because here's the question, people look at that computer and they almost always forget. Babbage couldn't build many of the things he imagined, right? Because, well, tolerances weren't as good for mechanical engineers, so we blame the mechanical engineers. But even if he had built them, at the cost of them at the time, it wouldn't have been practical. Why build a computer to do something you already had redundant, reliable, biological computers to solve? Because this is a little known fact. I know it sounds like something out of Doctor Who, but they had biologically based computers in the Victorian era. Were you guys aware of this? Yeah. They were people. You hired people to do the computation for you. Sorry, I better not get away from the microphone. You hire people to do the computation for you. So this device wasn't, if this device was intended to do calculations for you that a human being could do, what makes the data storage component an important part of it? The answer is, well, a human could do the sums for you, do the math for you, give you the nice answer. But then you take it to a guy who prints it, to print a book of logs for you. And what's he going to do is he's going to look at a table of numbers, and he's going to accidentally make a 6 into a 9, or move a decimal point over. And the net result is a ship's going to get wrecked on a reef as a result. So people would die as a result of this, were it not for the elimination of the human element in the transfer of the copying of the data. So it was the data management part of it that I would argue is the most critical part of an automated computing device. It's the preservation of that data. It's the reliable transmission of that data. So being able to store the volumes of data we create today and being able to do so reliably is arguably, I think, the most important thing ever. You should feel free to disagree with me on this, by the way, but I think it sets up a good premise for why we're talking about this today. Cool? All right. So, depending on your preference, I could talk a little bit more about the scale of this problem, or I could jump right into how we store data reliably. What would you guys prefer? Are you aware of the scale? Yeah, we all are. We got a good picture of it. I'm not getting a clear answer here. All right, I will show you just one of my favorite pictures on this. Yep, it's this one. It's coming. So this was back from 2009, I believe. This was about a year or so after Facebook started saying you could upload photos. And they said, upload photos to Facebook. This was several years after this service called Flickr had been around for a while, and it was like the place to upload your photos, but then Facebook said, yeah, upload your photos. We'll make it easy for you. We won't charge you for it. Then what happened? So this is the accumulated volume of all photos that Flickr had. This is all the photos Facebook got in that year, right, compared to that. So you'll notice that there's a pixel here, a tiny, tiny little pixel here. In the blowout, that pixel is this. That's the volume of data that also new service called Instagram that had just launched a few months before had. So you can see it was eating up into the amount of volume that Flickr had. But there's a pixel in that after you blow it out. Can you guess what that is? That is the entire Library of Congress image archive. Okay, so when we talk about data growing, like I said, not cat videos, but it's people in a funicular taking photographs in the dark with flashes and uploading them to Facebook. It's really ridiculous. But we throw around terms. We throw around terms like petabyte, exabyte, and zettabyte, right? Those are the sizes beyond. So petabyte is the size beyond terabyte. Right, it's the one just after that. Exabyte is the one after that, and zettabyte is the one after that. Once upon a time, people would tell you, oh, we generate a few exabytes a year. 2010, we generated 1.2 zettabytes of new data in that year alone. And to give you an idea of that, there was a very fun graphic I used to like, which was comparing a stack of first-generation iPads next to the world's tallest buildings. A petabyte would be superseded only by the Burj Dubai. Okay, an exabyte, if you wanted to represent the 1.2 zettabytes that were generated in 1 year, the mechanical and civil engineers would frown at you if you suggested stacking iPads like that. So they'd say, you want a wider base. So a wide enough base would be perhaps Wembley Stadium. Take a good-sized soccer field, right, via stadium. Fill it with iPads, then stack up. To get 1.2 zettabytes of first-generation iPads, you would need that stack to go 4.24 miles up into the sky. Right. That's what happened in the difference between the amount of data we generated in a year in over the difference in just 5 years. That's the difference in scale we see. So I hope I've convinced you that it's a good problem to look at. Right. Now, what I'd like to convince you about is that it's a good thing to look at it in terms of system software. So yeah, this photo is there because I wanted to point out what an operating system looked like. I particularly like the dress and the glasses. Okay, because what a modern operating system does, what your modern middleware does, what your modern cloud platform does, used to be manually done by the operators of the machine room. Right, so there's a lot of automation that's needed to make things scale like that. But here's the real reason I like working on system software, because it allows me to lie a lot. Okay? And one way to remain a perfectly honest person in your regular life is to find an outlet for all the deception and deceit you want. And I find that in, I'm joking, of course, in real life as well. System software, what does it do? It lies. Right? Well, we phrase that as saying you abstract away the underlying system and provide a simpler or more efficient representation of what's underneath, right? That's what we say. But another way of looking at that is, he has a device, he has a device. We want 2 devices worth of work, but they're not using them all at the same time. So how about we have 2 devices, only use one of them, and pretend that both of them are on all the time? What does this give us? It gives us a fallback device for the price of everyone just paying for one device. Sounds good, right? Except if they know, well, they should know, but if they feel a difference because of that, that's a problem. If we want to get efficiencies of scale, we want to have bigger data centers. We want to have bigger storage systems. Those cat videos are not living on my 2 terabyte drive, I'm sorry. If it's not for Google, if it's not for YouTube, if it's not for Facebook, they wouldn't have a place to live. But they do need to live somewhere. So where is that somewhere? Now, the question becomes, how do we make many devices act like a system that is more reliable than any individual device, that provides a capacity hopefully near the sum of their parts or some reasonable multiple thereof, and yet at the same time not have it break when it gets too big? How do we do that, right? So that's going to be the next part of this talk, unless you have any questions as to the motivation of why we're discussing this. We're good on that? All right. So I'm going to skip ahead to an illustrative diagram I'd like to point out. Okay. What some of the trends you'll see as you build larger and larger storage systems is you'll have more disks. Is that a surprise? No. But what do I mean by more disks? Tens of thousands or hundreds of thousands? I'm not sure. Overall, millions. How are they going to be distributed? How big is an individual data center going to be? Again, I'm not sure. I'd like a system that would be flexible enough to scale up as needed. Okay? But having more disks introduces a couple of really interesting questions that come to mind. When your disk fails, has anyone here had a disk failure happen to them? Yeah, we all have, right? If you haven't, prepare for it, okay? But how did your disk fail? What happened?
The operating system wasn't working with the hardware correctly and somehow caused a failure.
Yeah, but what did the failure look like to you? Because there's multiple different modes of failure, right? There is, I'm broken, I'm not going to work. That's one, right? That's how hard drives fail, right? They break and they tell you, sorry, can't satisfy that request. Sector read error, sorry, your data's not there. What they don't do, and you should really be thankful they don't do this, is they don't go and say, here's your data, and you're like, that's not my data. That never happens to you. And that never happens to you because of the way they're constructed. They're constructed with checksums on the sectors. They have error checking and error correcting codes in there. The likelihood of a silent error happening on a drive is infinitesimally small, right? What we expect is an error that happens and the device fails. So that's what we plan for. Did you notice I said the likelihood of a silent error is small? I didn't say it's impossible. Okay? That's too big of a problem for me to tackle right now. But what I will tackle is the following idea. If your hard drive fails, do you expect all the hard drives in your house to fail at the same time, or just one? Just one. So if you have 2 copies of your data, you should be good. You could get the backup out, restore it to a new drive, and you're fine. The only time you're in trouble is if both the primary copy and the backup copy get damaged somehow. Do we agree on this? That's if it's you and you have a drive or a drive array or a NAS box and maybe a backup drive and backup array in your home. That's about it. What if you had 20 drives? What are the odds of 2 of them failing at the same time? If any of you have children, the odds are, or pets, aside from physical damage, right? That can be a bad thing. So as the number goes up, if we go from a handful to a few tens to a few thousands, we start going away from the model of a drive might fail to how many drives are going to fail today? That becomes your concern now. How many are going to fail today? So our usual solution to a problem like this is to, you want to upgrade your storage to a more reliable model. What do? This is practical consumer advice here. This is not science. This is just practical shopping advice. What do you buy if you want to not lose your data? Redundancy. You buy a second drive, right? Or if you want to get really fancy, you buy a RAID array, right? So you get redundancy in one form or another. A dear colleague of mine likes to put it, RAID arrays are for those too cheap to buy extra copies of everything, right? To duplicate to mirror their data. But that's actually not true. Because I want you to think of this here. Here I have 3 data disks. My data is stored on these 3 disks because 1 disk wasn't enough for all the cat videos. I needed 3. In the scenario in the upper left here, I have a duplicate copy of every one of those drives. Now, what a RAID array would do is it would say, look, a drive is going to fail. You're going to know about it. So here's what I'll do. I'll calculate parity across your drives. So I'll take the XOR of all of them, shall we say, and I'll dump it on this extra drive here. That way you get 5 of them you get to use them. That's better, right? So that's what my colleague meant by RAID is for those too cheap to duplicate their data. They meant that you could get away with less redundancy, but you survive a less catastrophic event. His idea was, look, you want to be really, really sure? Double up on everything. Triple up on everything if you can. That way, if you lose half of them, you're good. He is, of course, completely wrong. And here's why. I can lose half these drives. I can lose these 3 copies, and I'd still be okay. A RAID array, if I lost RAID 0 through 5, and not including RAID 6, I could lose 1 of these, I'd be fine. I lose 2, I've lost data. If I had a RAID 6 array, I could lose 2, I haven't lost data. But pay attention to this example at the bottom of the board. It's quite different. What I'm doing here is I'm saying, here's a disk, here's a disk, here's a disk. So still 3 disks worth of data. Here's still 3 disks worth of redundancy. But the redundancy here isn't the direct copy of each of these. It's like a cheapo pairwise RAID arrangement. It's this guy and this guy's parity goes here. This guy and this guy's parity goes here. This guy and this guy and this guy's parity goes here. So every pair gets their parity on one of the 3 disks. I've not used more space, have I? And yet, that is more reliable than that. How? Well, you can see how you can lose any one disk here and you'd be fine. You could lose most 2 disks here and you'd be fine. You could even lose 1 combination, 3 combinations of 3 disks and you'd be fine. Specifically, you could use all these 3, triangle upwards, triangle downwards. You could lose those 3 combinations. What will kill you, though, is if you lose 1 and 1, if you lose any matched pair. So you can still lose 2 devices, and you're in trouble. Here, you can't lose 2 devices and be in trouble. If you doubt that, lose disk 3 and its copy in the upper example, you're in trouble. Lose disk 3 and any one of these, and you will always have a remaining parity disk that includes 3 that you can use to recover 3. So there is something beyond just doubling up your data, just making extra copies. There are ways to build models that are more resilient than that, is the point of this simple example. Sorry. So really, the only thing that would lose you data in this second example is if you find every disk that has a trace of 1, for example, and remove it. So you need a pattern of 3 that happens to get rid of all the 1s, or a pattern of 3 that gets rid of all the 3s, or a pattern of 3 that gets rid of all the 2s. And it would have to be that pattern. Anything else, you'd still be able to recover. So why is this relevant to us? This is relevant to us because it tells us that there is scope for improvement and flexibility in how you design a parity-based redundancy model for the data you store, especially if you have a large number of disks to work with. So, if you will allow me to you know what, I will skip over this. Are you interested in the mathematical analysis as to how we compare the probability of the two? I'd be happy to go into that. Yeah, a little bit? Okay, so one way to look at it would be to just use a Markov model of how likely you are to be in a state of 1 disk lost, no data loss, 2 disk lost, no data loss, 3 disk lost, no data loss. So in this previous example, we would have, if you have 0 disks lost, you could lose any one of the other two, disks, and you would have a state of 1 disk lost, but then you'd have 4 combinations wherein the loss of any one disk will cost you data loss. But you can survive from a state of one disk lost. Now, another example would be if you had the ability to survive all triple disk failures. You could exist in a state where you were, you had 3 disk failures and you're okay, but then out of those 3, you lose any one disk, you go into a state of data loss. So lambda here is the rate at which you lose disks, the failure rate of an individual device. So it's multiplied by the number of active devices you have currently that you're worried about failing. Mu is the repair rate. So how reliable your system is as a whole is not just a function of how reliable the individual components are, but it's also a function of how quickly you can repair them. Now this becomes very, very relevant in a second because, bear with me, the models for the diagram I showed earlier were not as simple, you can survive this many, you can survive this many. There were cases where you could survive a combination of 3 disks failing and you'd be okay, but that would only be for a subset of all possible combinations. So that's the case where you lose 3 disks but haven't lost data. Then for the cases where you have a subset where you lose 3 disks and have lost data, only for those 4 situations do you actually wind up losing data there. So the problem in doing the analysis for this is counting out the number of states that result in data loss. For these examples, it was done by hand and it was quite tedious. But the nice thing is that it provides a fairly tractable, simple Markov model that you can then solve to give you a mean time to data loss overall. Now, that is actually a point of concern. There are metrics for how likely a system is to remain reliable. One of the most popular is mean time to data loss. The problem with that is if I compare a system with a mean time to data loss of a year against another system with a mean time to data loss of 2 years, does that tell you that the one that is 2 years is twice as good? Sounds that way, but is it really? Right? So you may want to have a different measure. You may want to just know what is P, what is the probability of failure as a whole? Can you give me that? The answer is not that easily, but we did for a specific set of layouts. So if you will forgive me, because there's something else I think we're going to find a lot of fun that I'd love to get to. So what you're looking at here is the difference between those pairwise parities in terms of their mean time to data loss in years versus 3 mirrored pairs, basically completely everything doubled up. You'll see it's like 2 to 3 orders of magnitude better in terms of mean time to data loss. But the reason I have a concern there is I can't just throw out that number and tell you that means it's 3 times better. Because at some point there is the probability of a meteor hitting, right? And that's not factored into this model. So you can't do a simple apples to apples comparison that way. But it gives you a feel for this is stronger than that. That's really its main value there, okay? So I'm going to skip over that and I'm going to say, well, hang on. This pairwise parity arrangement, this can't be free. You can't get the extra strength for nothing. And the answer is, of course it's not free. It comes at a huge cost. Every time you update one disk, you have to update 2 other disks. So you're doing more updates. That's more active devices. You just sacrifice energy and maximum throughput in exchange for a more resilient system. Is it worth it to you? The answer is, it depends. Maybe it is, maybe it isn't. But you want the flexibility to be able to design more robust systems, right? Okay, so what you're looking at here is going nuts with pairwise parity between 4 drives. How many pairs can you arrange? And the answer is quite a few. But you can see something rather interesting in this arrangement. The reason I laid it out as a half a square like this is you can see the pairs 4 with 8, 2 with 4, and 1 with 2 would give you these individual disks here. But what if you wanted to get 2 with 8? How would you get that? How would you get the parity of 2 with 8? The answer is you could take the data disk 2 and the data disk 8 and calculate their pairwise parity, or you could take the parity of these 2. So depending on how you construct the file system on top of a system like this, if you can stage the updates so that they're always appends, they're always attached to a log, they're always add more data and not overwrite a lot, what you can do is you can make your system more reliable over time. How? You can sacrifice some performance by calculating this parity immediately, but you can calculate these extra parity ones later. Stage them. Can we afford to do this? The answer again is depends. Depends on the system you build. But when you start thinking about different ways you can arrange your data, all sorts of creative patterns can come up. Cool? All right.
Can I ask you a question?
Yes.
What do they do in the, let's say, cloud, where you have so many disks and so forth? And what would be the practical way of doing that?
So this is actually a pet peeve of mine, because a current practical way of doing it is for somebody to tell you the following. Look, I've got big system. How do I build it? I build it out of more reliable individual pieces. How? You're worried about losing 2 disks at the same time? Use RAID 6. That way it'll survive 2 disks failing. Then build your system out of many pieces, each one RAID 6. But, yeah, that's how you would do it now. And then you'd say, well, this is my site. I have very low likelihood of losing data within this one site. But you know what? Just in case there's a big disaster, because now we're factoring in the possibility of a meteor, a flood, an earthquake, a fire, we have a disaster recovery plan and we make a backup of the whole site on a remote system. So that's how practically you do it now. But my argument is, that's not the most efficient way to make your storage arrangement as strong as possible, and it's not as flexible as something I will point out in just a second. But does that answer your?
Yeah.
Excellent. So, patterns like this. How many crazy patterns? Well, the amazing thing about this is you can survive a ridiculous number of disks being lost. What you can't survive in this particular arrangement is the loss of all 4 data disks. That would cause you a problem. But if you instead switch from pairwise parity to 3-way parity, you can survive the loss of all those disks, because you have an odd number, so you can wind up with a mismatch. Yes?
I'm sitting here, I'm not quite sure what you mean by the XOR parity. And so maybe everyone else.
No. That's my mistake. I should have clarified that. So it's a very, very simple function. It's the one that hobbled the perceptron, because it was 1 XOR 0 equals 1, 0 XOR 0 equals 0, 1 XOR 1 equals 0, and 0 XOR 1 equals 1. So it's basically.
That's the truth table.
Yes, that's the truth table. That's pairwise parity. That's bitwise parity. It's an XOR function. So when I say parity, I mean calculating the XOR function across your bits.
Mm-hmm.
So you expand this out. If you're going to take parity across 2 items, it's just the pairwise truth table that you have there. If you're doing it for 3, it's the same deal, except expanded out for 1 more unit here. So what's the parity? What's the XOR function really? It basically says if you have an odd number of 1s, you get a 1. If you have an even number of 1s or all 0s, you get a 0. So what it does for us is it allows us to do the following. If I have the full truth table and I lose any one element, I can always figure out what I lost with just the remaining 2. Does
Okay,
that?
thank you.
You got it. I'm sorry for just skipping over that like that. All right. So what's happening here is these are just other patterns where you're looking at what you could survive. Can I ask you to trust me that you can survive quite a lot of patterns? Yeah? Okay, because I do want to skip ahead to something quite a bit, quite a few slides down from here. So, the patterns you can get, so this is what would happen if you started taking parity between 3 data items. So you would take 1, 2, and 4, for example, to get this one, 2, 4, and 8 to get this one, 4, 8, and 1 to get that one, and then 1, 2, and 8 to get the last one there. That is one possible pattern you could use. It's not particularly special, except in the fact that since it uses 3 contributing data disks, you can, for some of these arrangements, you can lose all of the 4 data disks and recover them. The reason you can't recover if you only have pairwise parity is because if you have a pair and a pair, you always wind up with a matched pair, so you wind up getting 0, you wind up getting nothing. So you always want to have one left over, which is the one you're looking for in that function. Okay. It's mathematical curiosity, not particularly earth-shattering in any particular way. But let me skip over that. Oh, so you can go totally nuts with the patterns, and early examples of this particular kind of scheme, we used to call it spiral arrangements of the data, and that's why. Because you can look at it and you can see these lovely spiral patterns when you expand them out. These are not practical, because you'd go to somebody and say, sacrifice 3/4 of your storage capacity for little extra reliability. It doesn't go over well. Okay, so a more interesting thing is Rasar, which is the culmination of this work for us, really, and it's where we wrapped it up with what we think are our best patterns to date. Rasar is an acronym that was chosen because the letters stand for robust, efficient, scalable, autonomous, and reliable. Sounds great, right? Sounds really, really good. But I have to confess the real reason for the name. My colleague, Professor Thomas Schwartz, is a much, much more learned man than I. And he pointed out that Rasar is the Catalan word for prayer, as in praying your data doesn't get lost, right? And he's a very, very beloved colleague. He's a Jesuit priest who's currently with Marquette University, but at the time he'd worked extensively in South and Central America. And he speaks far more language. He speaks more languages than I do, which is why he pointed that out to me. Okay, so with Rasar, our goal was, I really don't want to read slides of text at you. Our goal was to come up with schemes that allowed you to build reliable, very scalable systems. And we wanted to build on this idea of patterns that weren't traditional, that extended throughout your data. So what we did was, we did 2 things. One was we came up with a better pattern, but the other thing we did, which was really, really important, was that we stopped looking at individual disks. We didn't divide the data into, here's your disk 1, here's your disk 2, here's your disk 3. We said, look, here's your disk. Your disk is made up of 1,000 disklets, or 100 disklets. Why? Well, because then we could draw the pattern between the disklets, subparts of a disk. I know what you're thinking, this is silly, because if I take disklet 1, disklet 2, and disklet 3, and put the redundant parity for them on the same disk, what have I done? I lose that disk, I lose everything, right? Well, so yeah, so you don't put the same disklets that are part of the same pattern don't go on the same disk, but a disk is still divided into disklets. And this is actually not a technique of our invention, but it's a very practical technique used called declustering your data. And what it gives you is the ability to do this. You just lost a drive. How do you reconstruct it? The answer is you don't reconstruct it. You reconstruct all the disklets that were on it, which you can now do in parallel on as many free disks as you have available to you. So if you're a massive data center with tens of thousands of disks, and you just lost a drive that had 100 disklets on it, you can recover that entire drive in parallel to 100 disks. And now you've gotten everyone's data back super fast. So, what do I mean by super fast? Well, let me first explain how our patterns differed from those patterns you just saw earlier. Instead of figuring out the pairwise parity of the individual disks and labeling them, here's what you do. Let's take this example. This example has 16 data disks, and it has 4 parity disks and another set of 4 parity disks, meaning that you can lose any 2 disks in this example and still recover from it. So it's as good as a RAID 6, this one is. Now, you can draw this same diagram as a graph where the parity disks are nodes and the data disks are the edges between them. Because what does that mean? Well, a data disk being between 2 parity disks is its actual location in this grid, isn't it? So each disk is actually located between 2 specific parity disks. So that's how you would interpret a diagram like this. And this allows you to build a very, very nice pattern. It also allows you to turn the problem of making sure 2 interdependent disklets aren't on the same device as a graph coloring problem, which is a fun problem. These are nice problems to solve. Theoreticians love these. So what does this mean for us? It means we can do a pattern like this. This is a bipartite graph pattern where the pattern just grows like a big ribbon. Now this is super reliable. It can survive the loss of any 2 disklets, but because you've declustered it across your drives, recovery is super, super fast. So what is super, super fast? Well, allow me to just skip over this part. This is how you determine failure patterns and how we calculated the probability of failure. What I want to skip ahead to is this, the average recovery time. This is for a system that has 1 million drives where each drive was divided up into 100 gigabyte disklets. The average recovery time, as you can see, hovered between 20 to 30 minutes, with some outliers going up to 60 minutes. That's a sub 1 hour recovery time. How long did it take you to restore your drive after it failed?
I couldn't restore it. I had to replace it.
Yeah, you didn't recover your data?
Well, no.
Oh, okay, sorry, I didn't mean to bring up painful memories there. Has anybody had to recover a whole hard drive recently? Well, I did a few months ago. It took me a day and a half. So 60 minutes, not bad, right? Three to 4 minutes if we bring the disklet size down to 20 gigabytes. So remember how the reliability of your system is a function of both the rate at which the devices fail, but the rate at which you can recover from a failure? So just by going down from individual disk units that are on the order of hundreds of gigabytes to on the order of tens of gigabytes, we bring down the repair time from an hour to 3 to 4 minutes. Okay, and that's already good. That hour was already good compared to what I would do at home to recover an entire drive. So what does it take to make a system more reliable? The answer is keep an open mind regarding how you construct a reliable pattern of data, and also keep an open mind regarding how it is you're going to recover the lost data. If you can leverage parallelism, if you are a large site, you have problems. And that problem is you have many drives failing per day, potentially. So if you are a large site, why don't you turn that problem into an asset? You have thousands of drives available, make your recovery times even better by using a pattern that doesn't involve you recovering an entire RAID 6 array by pulling out a rack and putting in a new one. Right? So that's what I would, that's my pitch to you right now. So before moving on to one other topic, because I did promise to talk about shingle disks, which I can probably wrap up very quickly in the last 10 minutes, maybe 5 minutes extra if we can. Thank you. So here I have a challenge for you guys. Anyone here a fan of Tom Sawyer, the story? Not really. My favorite bit is where he tricks people into painting the fence. Right? He's being punished, and he turns that into an asset and has other people paint the fence for him. I think he would have been a great operating systems guy. Okay, so here's what I want to do. I would like to draw a thin line using a thick brush. Can that be done? Yeah? How? Imagine I want to draw a line with this thing. How can I draw a thin line with this?
Just use the corner.
Use the corner. Okay, this is a great big squishy sphere. And it will only write when I squish it hard against the board. So there's no corner to it. Yes?
You could do 3 passes where you do the first one and then 2 above and below it. That kind of erase.
Oh, I like how you're thinking. So you're saying, right, thick line. Then write, thick line number 2. Then write, thick line number 3. Thereby, you've erased this part, you've erased that part, and you've written a thin line. Is that? Thank you for inventing shingled magnetic recording. Because really, that's what you've just done. Here's why. One of the weirdest problems you have is that we face something called the media trilemma. Let me bring this up. Okay, what is the media trilemma? It is a struggle between thermal stability, media writability, signal-to-noise ratio, and definition. Big words meaning little magnets are difficult to keep in place. Okay? What do I mean by that? Once upon a time, a very, very clever scientist predicted that the maximum capacity of a magnetic hard drive would be no more than 60 gigabits per square inch. Right? And why did he predict this? Because imagine the ones and zeros you write as little bar magnets. North-south, south-north, south-north. You notice this bar magnet is pointing in a different direction from the others, right? So we're going to say this guy's a 0, this guy's a 1, this guy's a 1. Now, in any peer environment, when your peers want one thing and you want something else, you feel pressure to be like them. We are all familiar with this concept, right? Everyone wants to fit in. That's true for this 0 as well. Because it's a bar magnet with its south pointing to this guy's south, its north pointing to this guy's north. And you may say, no, maybe it has a better personality. Maybe it'll convince them to switch. But here's the challenge faced by this poor 0. This guy is also a 1. And this guy, guess what he's got on his side? A 1. So the 1 is, my north backs up your south. My south backs up your north. Look at that poor guy in the middle there. He has no hope. He's going to flip. It's only a matter of time, right? Well, no. Thankfully, your magnetic medium has many molecules. Lots and lots of molecules. So this guy is not alone. He's not 1, 0. He's an army of zeros in their own little island. But when your 1s and 0s on your hard drive start getting smaller and smaller and smaller, that army of zeros shrinks, becomes less and less and less. It becomes more like this guy, more like lonely 0 next to all the 1s. That's what's called the problem with thermal stability and definition. So you wind up with, when the zeros are so small, they're not going to be stable. The 1s are so small, they're not going to be stable. Whenever you get patterns like this, these are pushing him to flip. When he flips, what happens if this group is pushing another group to flip, and they're pushing them to flip? Your data has just been recorded on a device that over time just flips. This is no longer a storage device. This is a random number generator or of some kind. Not a very good random number generator, but still. So how do we make this better? The answer is we use a more thermally stable material. Because we all know what happens at absolute 0, right? Molecules just stay still. Right? We don't want them moving around. But we also don't want to have our hard drives at absolute 0. They're at room temperature. So we use a more thermally stable material. but that has a downside to it. A more thermally stable material goes up against writability. How strong a magnet do you need to flip the bits? Stronger magnet. The more stable it is, the stronger the magnet you need. But the stronger the magnet you need, the thicker the brush you're drawing with. And what was the point of this exercise? We want small bits, but we're drawing big bits. This is not good. This is circular. This is defeating its own purpose. So the prediction was, we're never going to get more than 60 gigabits per square inch because that's the limit. Beyond that, we can't write. Beyond that, we can't read. It's not going to be stable. Your average modern hard drive is over 500 gigabits per square inch. It's better than that. And it's better for that for a couple of reasons. One of which earned IBM a National Medal of Technology, I believe, which was the invention of something called the GMR head that allows it to read very, very tiny bits. But that doesn't fix the problem of writing. Okay? So how they fixed it initially was to do this. They said, this is your disk surface, right? Put some magic fairy dust on the disk surface and put 2 layers of magnetic medium. Not 1 layer. And your 0 is no longer a north-south. It's a north-south with a south-north underneath it. See, that one's backing that one up. And a 1 is a south-north with a north-south underneath it. So it's backing that one up. So if you ever hear the term AFM media in relation to your hard drive, that's what's going on. It's 2 layers with an antiferromagnetic layer in the middle. Magnetic material, non-magnetic material in the middle, and they call this sandwich here pixie dust. I thought the name was cute. But the point was that got things a little bit better. It made these things more stable. But it still didn't fix the problem with the big brush. It just meant you could use a less thermally stable material and get the bits down smaller, therefore use a weaker magnet. But how do we push it that one step further? And you had the key with the big paintbrush. Except instead of drawing above it and below it, I'm just going to draw above it. How? Like this. That's my read-write head, that big triangle up there. That glowing aura around it is its magnetic personality. It's writing, right? So what I'm going to do is I'm going to take that head and I'm going to reshape it so that the magnetic field is skewed. So I can have a more powerful field, but it's kind of skewed out that way. So I have a big wide brush painting this way. And here's what I'm going to do. I'm going to write a thick line. Then I'm going to write a thick line next to it after shifting the head slightly, leaving a thin line in my wake. So the reason this is called shingled magnetic recording is because it's like shingles on a roof. You lay one layer down, then the next layer down, then the next layer down. What this allows you to do is get your hard drive even denser. What this also provides you with is a great opportunity to write cool system software. Why? Because what happens when you want to overwrite this thin line here and all you got's a big brush? You're going to erase all the lines next to it. Unlike shingles on a roof, if you try to replace the ones on top, you have to remove the ones above that, before that, before that, and before you know it, you've gone all the way up the roof. You can't do that. So the solution is you lie. That is the solution. It's a very simple solution. So Bob comes to you and says, hey, Ahmed, I want to overwrite line number 2. You tell Bob, sure thing, Bob. Here's line number 2. It's like, that's not line number 2, that's line number 74. It's like, no, it's 2, trust me. Next time you ask for line number 2, that's where I'm going to read. What do you care? That's what I'm going to do. Now, I know what you're thinking. You're thinking, I just wasted some space here. Yeah, but I can reclaim this later. I can keep wasting some space for a while. Remember, I've got a bigger drive now to work with. So the point I'm getting at with this is you're probably, if you buy a really big drive now and it's fairly inexpensive, you're probably using this technology already. The reason you wouldn't notice it is because the drive is doing this lie, probably internally. So that's the mode wherein the drive pretends to be a traditional drive and everything seems to work normally. But if you think about it for a second, there's opportunities for you to use the drive a bit more creatively if you are aware of this stuff going on. Because if you're writing the file system on top of this, and let's say, for example, you're the guy who wants to build a big, reliable storage system, and you want to introduce snapshots of prior data, right? How do you keep old copies of prior data? The way you do it now is you'd rename the file, you create a new copy of the file, and you set aside the old copy somewhere in a hidden directory or something, or do something like that. But if you knew that this was happening, what you do is you'd write the new data, but keep the old data. But you're keeping the old data anyway. So you see how there's an opportunity there to leverage the nature of this drive? There are also opportunities for, well, if the drive is trying to be clever about the lies, but you really don't care about the data here, then you're better off just destroying it. But how's the drive to know that? The answer is it can't. But if you instead build a drive that instead of exporting an old interface to a drive where it's overwrite blocks, overwrite tracks, you export an object model for the drive, like the kinetic drives that Seagate released recently. There you tell it, save an object here, which is basically a file. Here's its ID. I don't care how you do it the best way that's optimal for you. If you know that the drive is weird on the inside like that, there are ways you can leverage that. So you get more capacity. You get a more reliable system. You get a more efficient system. You get a better data recovery plan and a cheaper implementation of versioning. All for free. No. You pay a cost, of course. Are there any questions, doubts, concerns?
Yes. First of all, in this case, it seems that we have some redundancy now. In case there is a crash on the top, then is it possible that we can use
I wish that were true, but this is at the level of how the ones and zeros actually look.
Right.
So a 1 needs to look like this. So if you were to lose this, you've lost the 1. So I wish I could say yes, that gives you more redundancy, but you've paid for that in terms of the extra density you got.
Right. Yeah. Okay. And then in that example, isn't it what the defragmentation, when you are doing the defragmentation, isn't it one way of expressing it?
Very, very good. So there are many tasks we do wherein a file system can get inefficient and you want to defragment it, for example. If you were using a long-structured file system, that's one where you would have to do garbage collection anyway. You would have to do compaction and garbage collection, which is exactly how you would solve this problem. So yes, if you could combine it with that, then it's the penalty for getting this is much lower. Yes?
Yeah, my question involves long-term archiving data. You showed an example of a really good archiving system, the hieroglyphics. But what is the state of the art now in terms of electronics?
Oh, I'm not sure I'm qualified to really answer that. Because when you think about it, how have we been tested? We have situations where there is government data that exists on media for which we have no replacements for the drives that can read them. So if you ask me what is the state of the art, in archives, the question is also what has been and continues to be the state of the art across the decades.
Yeah.
So if the question is, are we better at understanding the problem now? Yes. If your question to me is it a technical problem? I would argue no, not so much as it is a management problem. A good archival solution is more than just keeping the bits safe for a long time. It's having the infrastructure in place to be able to read it. It's having the software in place to be able to understand the formats. I will confess to something I hope is not repeated beyond this room. I wrote my master's thesis in Word. I wrote my doctoral dissertation in LaTeX. Can you guess which one I can read now? Yeah, I can recompile my doctoral dissertation now and get a fresh PDF. And it looks exactly the same and everything's fine. Mysteriously, my master's thesis is a different length when I open it in Word now. And the fonts don't quite look right. And the figures are kind of weird. What's happened? It was written in Word 2.0, by the way, if you're wondering. So it's the question with archival goes I think the challenges go beyond the physical maintenance of the data. The reason hieroglyphics worked so well is also in part due to the Rosetta Stone. If we didn't have that keystone to drape the code originally, we wouldn't be able to. It would be meaningless paintings on a wall to us. So your question is outstanding and far beyond my ability to answer adequately.
Thank you.
Any other questions? All right, so at this time, I would like to thank Dr. Amer for his very instructive and really the way that he presented it. I mean, it was really so interesting. I think we have all learned a lot out of it. Okay, so let's give him a hand there.